Hi, I'm Si Ben-Yaakov. This presentation is entitled Fundamentals of Silicon MOSFET Losses and Thermal Cooling in Power Electronic Systems, and this is part 1, Conduction Losses. There are some relevant videos to this presentation which sort of add more information. I'm going to put these links at the page of this video that you are now watching. So what is the problem we are addressing here? If you are passing current through a MOSFET, and this is the MOSFET with the TO220 package, there will be some heat generated because of the power dissipation or power loss within the transistor, and consequently the temperature will go up. Now this could be dangerous because there is a limit to the temperature of the junction. Once you approach it or pass it, the transistor will be damaged. I'm showing here a board with these transistors, as a matter of fact, 220 packaged transistors, which are without cooling. And here there is some current passing through them, not the nominal current, much lower than that. And we can see the heating of these transistors via this thermal camera. To remove the heat, we do need some cooling fixtures. And here is a simple block. This is like a heatsink without fins in this case, it's just a plate. Here is a block of aluminum. Here are the transistors which are attached to this block, and the heat is passing from the transistor to this block and then into this plate and then dissipated outside to the ambient. And here we see a steady state situation at which we are passing some power through the transistors, and there is a heat generated, and consequently the temperature goes up, and we see that it's the hot spot in this case is 79 degrees. This is an aluminum plate, so the gradient is not that much of the temperature. We see that the coldest point is 76, the highest is 79 because it's well conducting the heat. And by this we can actually remove the heat from the transistor to the ambient surrounding. Here is another example of a board which is in fact a three-phase inverter. You can judge from the thickness of the cable that this is for high current. In fact, it's for about 200 amp. And these transistors are put on the PCB, and there's going to be a heatsink above them. These are transistors which have cooling from both sides, so the heat can be removed efficiently from the transistor itself. This shows here how the temperature rises as the current is increasing, and we see this is the delta increase in temperature for this single particular transistor shown here. To further improve the cooling, there are some other means like a fan or a heatsink with fins that have a much larger surface area and therefore remove the heat much better. The transistor will be, of course, connected here to this side. It is important to realize that the question of MOSFET losses is not just a question of efficiency. In fact, efficiency is important, but that's not the major point. The major point, perhaps in many applications, is that heat removal is costly. It's increasing the size and the weight, and it requires additional air conditioning, in fact, in the room. Because if you have a unit which has a lot of losses, you have then to remove this heat from the ambient, and this is also costly and has to be taken into account. So the outline of this presentation, which has three parts to it, is, first of all, we look at the question of conduction losses in general and the concept of RMS. What is MOSFET conduction losses? And then in part 2, we'll talk about switching losses, including transition, the output capacitance effect, and then the diode reverse recovery losses. And in part 3, we're going to cover the issue of thermal cooling, showing some basic concept and an example. Now this presentation is primarily related to silicon MOSFET. There are some videos in my YouTube channel which are related to silicon carbide, and gallium nitride devices, and you're welcome to watch them, of course. So silicon MOSFET is the subject matter here, and let me just go over it very quickly. We recognize two types, the N channel and the P channel. Both of them do have internal or body diodes. We have normally gate voltages in the range of 15 to minus 15 or lower for the so-called logic level transistor. Now the N channel is usually preferred if possible because it's less expensive, it's more popular, and also it has a lower rds for the same die area. So this is preferred, except that sometimes driving it might be more complex. Now in looking at the static characteristic of a MOSFET, we recognize the typical MOSFET behavior. In switching, we are interested in this region here, in which sort of all the curves are sort of coming together for high enough gate to source voltages. 1 over this slope is defined as the RDS-on. This is a resistive behavior, a straight line between ID and VDS-on. And the RDS-on itself in modern transistor is in the range of, say, between 10 ohm down to 1 milliohm transistors. Now, if we look closer in here, we see that the RDS-on, that is the slope here, is dependent on VGS. The higher the VGS, the lower is RDS-on. This is RDS-on, this is milliohms, and here we see the RDS-on for 10 volts, and then 4.5, then the RDS-on is actually higher. There is also some dependence on the current, especially when the VGS is lower. At high VGS, 10 volt and above, for this particular transistor, then the current effect is less pronounced. Now, power MOSFETs are in fact built from paralleling many small MOSFET cells. So it's like a honeycomb, many units which are put on one die in order to be capable of carrying high current. In this particular case, this transistor can carry currents up to, say, 100 amp, which is quite remarkable. There is also a dependency on temperature. RDS-on for silicon MOSFET goes up with temperature. And if we look at the change between, say, 25 degrees and 150, 180, then it's about a factor of 2 to the maximum. So one has to take into account that as the transistor is heating up, RDS-on is in fact going up. This will be very typical for a silicon MOSFET. To get higher current, it is possible to parallel transistor, which is made possible by the fact that they have a positive temperature coefficient. So by this, if one transistor is starting to, say, carry more current, it's heating up, the resistance goes up, and therefore it's sort of self-balancing the current sharing between the parallel transistors. So this is a very nice behavior that allows putting transistor in parallel, and as we'll see, there is advantages to it. The issue of current sharing of parallel connected MOSFET is covered in this video, which will also be printed on the page of this YouTube video. Another important information is that if we look at the RDS-on of a transistor as a function of the blocking voltage, and this is of course for the same die size, then we will find that up to 500 volt there is a rise in RDS-on. That is, the higher the blocking voltage, the higher the RDS-on, but around 500 volt the rate of rise is much faster. So say a MOSFET for 1000 volt, and there are some transistors like that, would have a rather high RDS-on. So if possible to limit the operation to below 500 volt, this will provide the transistor with the lower RDS-on. I'm now going to cover the issue of power loss in a resistor, because the transistor, the MOSFET transistor, actually behaves as a resistor. So just to be on the same ground here, I'm going to discuss a little bit the concept of RMS and see how we deal with waveforms which are typical of PWM converters, for example. So we start off with, this is actually Ohm's law, and then the power is the product of voltage times current and then integral over a certain time. And then since V is I times R, I can replace it and I get I square. And then this is in fact the power, R times this integral. And then if I take this square root of this part here, which is defined as the RMS current, this would be like the equivalent, say, DC current that will cause the same power loss in the transistor as the original waveform. So this is the concept of RMS current, which is an equivalent that it's one number that you can use without actually going into all the details of the waveform. The question is how to get it, and this is what I'm going to do next, especially with relation to PWM pulses or waveform. Now, if we look at the conduction losses in the general case, if we have, say, an impedance, there is a voltage and current, then again, by definition, the power is the product of voltage times current, integral, and then divided by T. This will be the period. This will be the average power. Now, if I have some general form of a continuous waveform, I can break it into its Fourier components, cosine or sinus components, plus an average value. And then, of course, the power will be the product of this. Now, we know that when you take the integral of two cosine or sine functions of different frequencies, this integral is zero. This implies that you have a components of different frequency, only same frequencies, that is only if the V and I will have the same frequency, then they will contribute to the power. In the case of different frequencies, there will be no power involved, and therefore you have to take only into account products of same frequency signal, including the DC, which is considered like a zero frequency signal. And one more point here, if we have currents of different frequencies, I is different frequencies, and then the total power will be R passing through a resistor with the resistance times the sum of each one of these RMS, and therefore I can define the IRMS of this whole bundle as the square root of the sum of the square of this RMS current. And same thing will go in, I'll talk about the RMS voltage. And of course, we are talking about the case in which these frequencies, these I's, are of different frequencies and not the same. So let's see how we can use all this information in order to find out what is the RMS and eventual power loss in a resistor when we have waveforms which are typical of switch mode converters. So let's start off with pulses of this nature. We have on and off with the duty cycle, a given duty cycle. This is T on and not shown here. This is T off and this is the period. And then the power in this region is Im squared over R. Im is the maximum. And then the average current will be this area here divided by Ts, which is then the power times T on and divided by Ts. This is by definition the duty cycle. And then I represent it as R times I square, the maximum D on. And therefore, this thing here is related to the power, and it is the IRMS square by definition. And therefore, the RMS of this current is the peak value times the square root of d ohm. So once I have this waveform, I can very quickly find what will be the power, which will be, of course, this square times the resistance. Now, what about a triangular waveform? Here we have one section here which is repeated itself 4 times. Each one has the same area and the same RMS. So dealing with one of these, I found that if this is defined as the peak value, I'll not go into all the details. I find that the RMS is I peak over square root of 3. A sinusoidal waveform is square root of 2. This is square root of 3. And therefore, if I like to find the power dissipated in a transistor with a current with a peak, a triangular current with a peak value plus minus of I peak, then it'll be I peak square over 3 times R. So now we go into a real situation of a PWM signal. Suppose this is the current that is passing through a transistor, which is very typical. We have the slope here, which is due to the inductor. We have some T on and some T off. And how can we find the RMS value based on what we've just said? Well, there is a quick way to do it, and here it is. We first of all remove the distance here and assume that this is like a continuous waveform, and then we separate different frequencies in order to be able to use the concept that I've shown before. And we do it by taking this waveform and separating into a DC plus an AC component. It should be like this and not like this, because if this is DC and I'm sort of separating this waveform into a triangle like this, not an AC with an average 0, then this has a DC component, so these are not two different frequencies. So what I want to do is to get two different frequencies, and this is the way to do. This is DC and this is AC. Well, there are many frequencies there, but they are not like the DC value here. Once I do that, here it is, I can find, first of all, the average value here of this component of 0 frequency. This is I average square. And here we have a triangular waveform, and the I peak is this value, delta I over 2, and then over square root of 3 because it's the peak, and then square because I have to take I1 square plus I2 square, two different frequencies, and the RMS, of course, will be the square root of this value. But before that, I like to bring back this off time and take it into account by saying that if this is related to the power, then the average power here is times this duty cycle. Because I have some power here, if I multiply it by T on divided by Ts, this will be the average power here. So again, I'm multiplying it by D on, and therefore the RMS will be this square root of D on, I average square, plus this term for the AC component, for the ripple here. And I can express it a little bit different, like the IP minus delta I over 2. This is I peak minus half the deviation. So this is a very simple way to do it. So a silicon MOSFET in the switching region and the low voltage region is really behaving like a resistor. So I can now use the concept that I've shown before, so I can find what will be the power loss in the transistor by multiplying the RMS current of passing through it times the RDS on of the transistor that I'm getting from the datasheet, taking into account, of course, the increase due temperature rise. So here's an example, which I'll not go into the fine detail, just to show that we have here a boost converter with an input voltage of 25 volt, output 100 volt, power of 100 watt. I'm just talking about conduction losses of the MOSFET, and I'm doing it in an approximate way. So first of all, I'll find what is the duty cycle, and this can be found from the transfer function, transfer ratio of a boost converter, 1 over D off, and I find that for 100 kilohertz, the T off is 2.5 microsecond and T on is 7.5 microsecond. And then I can find what is the delta I from the T on, because during T on this transistor is on and the voltage is across the inductor. I find it to be 1 amp, and the average current is the power over V in. This is the average current going in here. It'll be 4 amp. So here is the waveform that the transistor is passing. This is the current of the transistor. It's average of 4 amp, and the ripple, rather small ripple of 1 amp peak to peak. So now plugging it into just the equation we've seen, I average is 4, and then this delta I can find out what is the power dissipation of the transistor. So this is a very simple way to find the conduction losses once I know the RDS on and once I know the waveform of the currents through the device. So this is the end of part 1. This is part 1 of 3 parts. I thank you very much for your attention. I hope you found it of interest, and you are welcome to watch part 2 and 3.